This is the problem about the building materials, and it says 3 building materials: plasterboard with a given K in the problem, brick with another K, and wood with yet another K are sandwiched together as the drawing illustrates. At temperatures at the inside and outside surface are 27 degrees Celsius and 0 degrees Celsius respectively. Each material has the same thickness and cross-sectional area. Find the temperature A at the plasterboard brick interface and B at the brick wood interface. Okay, I will not do the problem the way it's written out, and when I teach this in the classroom I always say that, I'm not really interested in what the temperature is in between here, but what I'm interested is how well do these 3 sandwiched together here insulate. So overall what I'm going to do is I'm going to calculate the so-called resistivity or conductivity of these 3 sandwiched building materials. So I'm going to do the problem differently with a different focus. I guess that could be a little bit bigger. There we go. Okay. What I'm going to determine is what is the overall conductivity. So that means I want to determine a K total or equivalent conductivity of these 3 materials, and I should specify that a little bit better because the conductivity depends on, well, the building material, but it also depends on the distance of each of these materials. I know they're saying they're of all of the same distance, but I would have to say that under normal circumstances you probably have different distances in between here. So I'm going to include that. I'm going to write what is the K over L of these here all sandwiched together. Okay, with that I have to look at what is actually happening here. Well, heat of course flows from here to here, but it first has to flow through this one, then this one, and then finally this one. And each of these building materials is trying to resist the heat flow, and that's the word I'm going to use, resistance. If you have seen perhaps in another class on DC physics, or took a very basic electricity class, you would be familiar with resistances in series, and when resistances are in series, then the equivalent resistance looks as such: R1 plus R2 plus R3 plus R4 and so on. So simply add the resistances in a series circuit. The same thing happens with thermal conductivity. After all, heat being conducted sounds almost the same as electricity being conducted. In fact, the equations are the same. So the heat encounters this resistance, and this resistance, the heat flow that is, and therefore we would add the resistances. Now, the way it turns out is that the resistance is what I'm looking at here, but what's given in all these equations here, or in this particular equation, is the conductivity, which of course is the reciprocal of the resistances. So this is the way I can write it. The equivalent resistance then is the equivalent conductivity 1 divided by, because it's the reciprocal of the resistance, and then plus the reciprocals of the others. And as I said, I want to include that L, even though they're implying here that they're all of the same distance, so that actually would divide itself out, but here I want to include it because what if you have some other kind of problem where L is given? I'm sorry. Yeah. The L's are different from one to the other one that are sandwiched together. So that's what I want to calculate. Yet following with this problem here, let's just assume that L is 1 unit. I don't want to call it 1 meter, but I'm just going to call it 1 unit. May that be a centimeter, or may that be a decimeter, which is 10 centimeters. So I assume that each one of these here is 1 unit for the L, and then we're just going to have ones here, and we're going to calculate. And that means that the resistance, the conductivity for each of these here is given as such in the book. So for the first one, it's 0.3 joules per second meters in Celsius degrees, 0.6 for this one, and 0.1 for this one here. Now, when we put them behind each other, we figure out that the insulation has increased, and that means that the conductivity has to go down. So whatever the result is here for the heat conductivity should become less, because that's the idea behind it. So as I said, the given K's are 0.3, 0.6, 0.1, and when we put them together, the overall result should be less than any one of them, so it should be less than 0.1. Okay, let me plug that into the calculator. As I said, I'm going to keep the L as 1 unit, so I'm going to have 1 divided by the first K, which is the 0.6, then plus 1 divided by, oops, that was actually 0.3, plus 1 divided by the 0.6, there it is, plus 1 divided by 0.1. And again, the 1 is in there because I said the L is a unit of, or has a value of 1 unit. So the right hand side being calculated is going to be 15. But I turn this around. This is the reciprocal, so I cannot compare this one here to any of the ones that are given in the book as KL equivalent. So I again take the reciprocal, KL, and the reciprocal of that 15 is 0.067, which indeed is smaller than any one of the others that are given. So, and then the units on this one here is joules divided by second meters Celsius degrees, and again some kind of unit here for the L here in meters or centimeters or what have you. I have to write that on here too. So this first part here can be readily compared, and as I said, the conductivity went down, which makes sense because we're sandwiching these together in series. The resistance, heat resistance, should move up. By the way, that 15 that I calculated a moment ago of the reciprocal, which actually is the resistance, could be kind of considered an R value. If you want to compare that to the real R value that you find in the store, well, you cannot use metric values here. You would have to get the joules into BTU and the meters into feet and the Celsius degrees into Fahrenheit in order to compare that. And here's the conversion. It's this one right here, the 0.176. So if I take that R value of 15 and I divide that by the 0.17611, I come up with a ridiculously large R value of 85. Notice the units here, the kelvins. It's of course the same as the Celsius degrees. You saw the square meter in there, and then the watt is the same as joules per second, and that is then transferred into these units which are underlying the R value. Now, as I said, I come up with 85 for the R value, so this one is equivalent to the American 85 R value, but remember I said for the L here I'm using an arbitrary 1 unit, and of course if I call that unit 1 meter, that's ridiculously large. So if I instead just use 10 centimeters, which means each one of them is 4 inches wide, then that value I just calculated from 85 is only 1/10 of that, 8.5. And here's a table that you can see some of these R values, 7, 8, 6, 5, 6, so it's kind of in that neighborhood. And lastly, here's actually the equation that I used in this problem, where when you have the multi-layered installation, so sandwiched, you come up with adding the resistances.